Hello everyone. Today I'm going to explain Dijkstra's algorithm and how to implement it. So first, apologies for any delays because this computer does not have a microphone, so I'm using Google Meet with my laptop, which is slower, so I'm not using that to record. All right, so if you don't know how Dijkstra's algorithm works, I will link a video in the description from Spanning Tree that explains how it works. Be sure you know how it works. Now, if you just came back from that video, I'm going to refer to the towns as nodes. Let's get started on the proof. And the reason I'm not linking a video to a proof is because all the videos I saw online are pretty ass. So I'm going to try to prove it myself, which hopefully is a bit better. So with Dijkstra's algorithm, you have a set of visited nodes, which we'll call V. I don't know why I wrote S. And you also have a set of unvisited nodes, which we'll call V complement. And between them, there is a one path that goes from visited to unvisited. Now, let me define some things first. So we're going to call D of U as the algorithm's distance to U at some specific point of time, and we're going to call this piano note. It looks like a piano note, but apparently I think it's delta. We're going to call delta U as the absolute shortest distance to U. Okay, so what we want to prove is that when we add a new element to the set of visited. So let's say we have these elements and maybe the Dijkstra values are 6, 7, and 8. By Dijkstra's algorithm, we're going to be adding this to the set of visited. And we want to prove that 6 is indeed the shortest distance to this node. How do we prove that? So we're going to prove this by induction, and we're going to assume that all of the nodes in the visited set already has the shortest distance. So in the visited set, we have a source node, we have some other nodes connected to the source node. Maybe we have these. I'm going to add one more. And what we're going to do, we're going to assume that these have the best possible distances. So the Dijkstra distance would be equal to the delta distance of these nodes. Now, the reason we can do that is because induction. And if we manage to prove that every time we add a new element to the set of visited, then it's the shortest path, then all of the visited things will have the best possible distance. Like it's how induction works. All right. Let's say that we have the visited set and it's connected to some nodes that are not visited, that are in the unvisited set. So we have these. Maybe there are multiple ways to get to one node, which we see here. I'm just going to, for learning purposes, I'm not going to draw too many lines. Let me draw one more. Okay. Where's my mouse? There it is. Okay. Let's label these Dijkstra distances as 7, 6, and 9. What can you say about the Dijkstra distances of these nodes? Well, if you think very hard about it, these Dijkstra distances of everything that's unvisited, let me just add a new node that's Dijkstra distance infinity. This property that they all have is that they are the shortest possible distance that connects directly from the visited set. So it's definitely possible to get to 7 faster, like if there was a distance from 6 to 7 with distance 0 or 0.1, doesn't really matter, then the shortest distance to this node would be 6 and not 7. What I'm trying to say is that the Dijkstra distance to this node is the shortest possible distance from the set of visited, meaning it's possible to get here faster, but then it will have to connect to the set of unvisited. And this makes intuitive sense because here, infinity, it just means that you can't get from the visited set to this node at all. Okay, now we need to move on to the proof. So the node we're adding is 6. Just like all the others, it is the shortest possible distance from the set of visited. Oh, I forgot to prove it. Well, the reason is because for every single node, for every single path that's connected to this node or any of these adjacent nodes, they would have updated this path. So recall that all of these nodes in the set of visited has the best possible path, and if they're connected to this node, then they would have updated this distance to be the shortest distance from the set of visited, and that's the proof. Okay, now we need to prove why when we add 6 that it's the shortest possible distance to that node. Let's say this node is called x. We're trying to prove that d of x is equal to delta of x. How do we prove that? Well, what we do is we assume that there's a shorter path. Let me just draw let's say you say there's a shorter path. Let me draw it. Maybe it starts at S and it goes somewhere. The thing is, it can't stay in the set V because we already know that 6 is the shortest possible path from the set of visited, meaning it has to leave the set of visited at some point. Maybe it leaves to here and then somehow connects to V. Maybe it'll even go back and then connect to V again. Doesn't really matter what happens, but what you know is that this path that is presumably, is that how you say the word? Presumably shorter? Is not shorter because this path that goes up to this node with Dijkstra value 9, if you chose the most optimal path to this node, then it would have distance 9, which is already bigger than 6. You've traveled 9 kilometers. You can't get to here in less than 6 if you've already traveled 9 kilometers. So if you chose the most optimal path to get to this node, it would be 9. And if you chose the less optimal path, then it would even be farther from getting to this node in a shorter distance. And this applies with any path that you might say, like this path. For example, if you go somewhere and then go to here and then get to 6, the same thing applies with this path. This distance right here with these all squiggles, and then you connect to this node, it would be bigger or equal to 7. And if you chose the most optimal path, which is getting here in 7 kilometers, it's already bigger than 6, meaning you can't get there faster. This applies with every single path that you might choose. And that means that 6 is the best possible distance. So when you add it to the set of visited, it's the best possible distance. Now I want to go through one more way to think of this. Okay, I want you to think of this as China trying to travel to Africa. So China is a set of visited and Africa is unvisited. Okay, let's say you're at this, is it called a state? I don't know if it's called a state. I'm just going to call it a mini country. So let's say you're at Qinghai and you've already traveled through all the stuff here, the mini countries, and you found the shortest possible distance to all of these. Recall that China is a visited set. So you found the shortest possible distance to all of these. And then because you're a communist, you want to invade Africa. So we're going to build these bridges to Africa. These bridges are thick. Okay. Boom. Maybe you want to go to Mali. Maybe there are multiple ways to get to Mali. Let me just put some of these. Okay. Now, actually, I should add a few more bridges for clarity. Okay, so let's say the Dijkstra distance to Botswana is 6, and then you might have 7 here and 8. So all of these distances, this distance would be the shorter path of the two. So this distance would be the shorter one of the best possible distance to here plus the length of this bridge, and the best possible distance to here plus the length of this bridge. And for example, if this one was shorter, then we would choose this mini country to have a distance value or Dijkstra distance of 8. Same applies with all of these. Now, this one has the shortest one. And what can you notice about them? What you can notice is that the best way to get to the unvisited set is like all of these countries will have a distance value or the best possible distance greater or equal to 6, because the most optimal way to get to Africa has a bridge length, has a length of 6. There's no way to get to Africa faster. Now, we can actually ignore all of these altogether and imagine the visited set as just one thing. And then we construct all the bridges like this. Okay, we're saying this has distance 6, meaning this bridge has distance 6, and then distance 7, distance 8, distance 9. So let's say you want to find a shorter path to Botswana. Well, that's not possible because first of all, you have to leave the visited set. And if you leave the set, you must go through one of these bridges. But all of these bridges already take a longer time than 6, meaning it's impossible to get to Botswana faster than 6 kilometers. And I really hope that you understood how Dijkstra's algorithm works, why it works, I mean. Because when I learned it, I did not understand the other explanations. Okay, now let's do an application. And I just want to make sure that I'm still recording. Okay. Let's do the application. Single source shortest path. You have 1,000 vertices and 5,000 bidirectional edges. What does bidirectional mean? It just means that if you can get from here to here, then you can also get from here back. Let me just clear everything here. Okay, so that's what bidirectional means. The input specifications is you first have n, which is how many nodes there are, starting from 1, 2, 3. From, or in other words, the next m lines, it's going to be a weight with from 1 to 10,000. That is a weight between node 1 and 2 is 2, node 1 and 3 is 5, node 2 and 3 is 2. Multiple edges between the same pair of vertices may occur in the input, so it's possible you have 1, 2, 2, and then 1, 2, and 5, meaning that you don't want to take in the 1, 2, and 5 because that's a longer way to get to the node. And the output specification, you want to output the distance between, or the shortest path from 1 to vertex I. If no path exists, output -1. Wait, where's my, okay, here we go. So the first thing, let's have adjacency matrix. Let me show you what it is. Adjacency matrix is a way to store distances from one node to another. So I'm not using this because I've already seen this and there has been an issue with it. Namely, he copied it wrong. So if you want to take a look, he copied, this should be a 6 here. He copied it wrong. Same with the other ones here. Okay, so let's take a look at another one. So we're going to use a 2D array to store the distances from one node to another, and 0 would indicate that you can't get from that node to another. Now these nodes are indexed as 0. It's going to be different in our case, but for this we can still look at it. So the distance between 0 and 2 is 3, and it reflects on this 2D array. This distance from 0 to 2 is 3. You can also look at it the other way. Distance from 0 to 2 is 3. Okay, so we're going to store these in an adjacency matrix. It's going to be called distance from one node to another, and it's going to have a size of 1001. And I don't want to type 1001 every single time, so I'm just going to call constant bruh equals 1001, and I'm also going to need an infinity, which is 2 billion, because 2 billion is large enough, and you'll see why I will need infinity later. I mean, you've seen how Dijkstra's algorithm works, so I think you should know. Okay, so we're going to have a 2D array that stores the distance from one node to another. We're also going to have a visited array, and we're going to need a, what is it? Oh, the minimum distance to a node, which we'll call min. You're also going to store the number of nodes in a global variable because we'll be using functions that are needed and in the global scope. So first, we'll do how many edges it's taking in, and we're going to take in the value n and then q, and then we're going to loop through q times. And what while q minus minus does is the same thing as for int I is equal to 0. What the hell? I is not equal to q, I plus plus. The only difference is you're not initializing a new variable I. So I'm just going to do while q minus minus is shorter that way. It's going to take in a node 1, node 2, and a distance. And we're going to set the distance from node 1 to node 2 to the distance from node 2 to node 1 and equal to d. Now there's one problem because we're updating this node 1 to node 2 to be the latest value of d, and which means that if d was bigger, you would be updating it to a bigger value, and you don't want that. So we're going to set a condition if we have already updated the value. And by the way, all these are initialized to 0 because it's in a global scope, and I don't know why, but it's initialized to 0. So if it's not 0, if the distance from n to n2 is not 0, it means what is going on here? If it's not 0, that means we have updated before, and if we have updated before and the distance is smaller than the distance before, then we will update it. Okay, let me just copy this code. Otherwise, it will do nothing. What's going on here? Oh, it's uninitialized, so we need to take in the variables. Okay, so this is what? Whoopsies, sorry guys. Okay. And if it's equal to 0, then we'll update the distance. Okay, and also we don't even need that here. Okay, so we have taken in all the values of the distances. The next thing we need to do is set all the minimum distances to infinity. So we're going to use a function called fill, and we're going to start from min to min plus n plus 1, because it's starting index at 1, so we need the array going from 1 to n, and we're going to fill it with infinity. Now, if you don't know how this works, you can also do for int I is equal to 0, I is not equal to n plus 1, I plus plus, min at I is equal to infinity, something like that, but I'm not going to do that. And then we're going to call the Dijkstra function, which we'll add right here, void Dijkstra. Here, oh, by the way, we need to set the minimum distance to 1 as 0 because the distance from 1 to 1 is 0. Okay. Now, imagine Dijkstra. Imagine how it works. Okay. I'm not going to put the 2 loops yet because it might be hard to understand, so I'm going to do it step by step. The first thing you want to do is you're going to set the node you're looking at as 1 because that currently is the shortest possible distance from the unvisited set, and then you're going to visit it. So you're going to set it to true. Next, you're going to loop through all of 1's neighbors. So for int I is equal to 1, I is not equal to n plus 1, I plus plus, you're going to loop through all the neighbors. So number 1, it has to be possible that you can get there. So the distance cannot be 0 if distance from u to I is not equal to 0. And by the way, a shorter way to write this is just delete that overall. And it's not visited because recall, if it's already visited, that means it already has shortest possible distance as we have proven earlier. So, and it's not visited, and the new distance, so min at I, min at u plus distance from u to I, shorter than the distance before to I, and we're going to update the value of I to be min u plus distance from u to I. And then what we're going to do, we're going to select another one from the unvisited set. So let me pull up my whiteboard. You're going to when we have a source node, we have updated all of its neighbors, and then we'll be looking at the shortest one of all of them. So we're going to actually need a function called min index, which gives you the index of the minimum node. So let's create that up here. Void min, int min index. And we're going to have a int m and oi. This is trivial stuff, I think, so I'm not going to say anything. Oh, wait. Okay, first of all, it can't be visited because if you include the visited, it's just going to visit 1 again, and that's not what you want. So if it's not visited and the distance, the minimum distance to I is smaller than oi, then we're going to update oi is equal to minimum I, and update m is equal to I, and then return I. Oh, you return m. But notice that you can actually optimize it, but you don't need this at all. And all you need to do is change this to a 0, change this to a min m, and delete this. And the reason this works is because, I need to use that. The reason this works is because min of 0 is equal to infinity, so you'll be comparing right off the start. Okay, and then you're going to set u as visited, and then you're going to loop through all of its neighbors. And you can see it's actually getting quite repetitive. I can copy paste this code here. So what you need to do is you need to have a double for loop. How many times should the for loop repeat? Well, at first glance, it should repeat n times because there are n nodes. And you are quite right. There can be you only have to loop it in n-1 times, but n times does not matter. You can also loop it n times. The reason you can loop it n times is because n-1 times is because when you have the last node, so you have visited and unvisited, if we only have one node left, it has been updated by literally everything, and it also has no neighbors. So it's going to have the shortest distance, meaning you only have to run it n-1 times. Okay, so what else do we have to do here? You can actually do one more optimization saying if min at u is equal to infinity, then break, because that would mean it's impossible to get to the other nodes. But let me show you that it works without it anyways. Okay, now we need to have the output, which is print -1 if it's not possible, otherwise print the minimum distance. So we're going to do for int I is equal to 1, I is not equal to n plus 1, I plus plus, and if min of I is equal to infinity, then std cout -1, else std cout min I. Let's see if it works. Where are my browser tabs? Oh. It's possible it doesn't work and you might need to do some debugging. Oh, it does work. Okay, let's test it on the DMOJ. Great, it works. Let's see how much slower it would be if I didn't have... Oh, let's say how much faster it would be if I had that. I mean, in theory, it should be faster, right? Okay, it's quite... I mean, it is faster. You can get it faster using sync with Studio if you turn it off so it doesn't sync with the C Studio, and you can also tie so that it doesn't flush the buffer every single time it's reading in something. Okay, much faster. That's it for today. There is also a better way, or there's also a faster way using priority queue, I believe, which orders everything from greatest to least, meaning you have to reverse the order using negative numbers. Okay, just imagine a queue that is always ordered from the minimum to the greatest, so you don't have to do this min index every time, which takes O of n time, which is long. I think there's a shorter way, log n time or n log n, I'm not sure. So there are shorter ways to do Dijkstra, but this should be the most intuitive way, and I hope you understand this lesson. Thanks for watching.